In this problem, we're going to look at two bars constrained between two walls and apply a change in temperature to the system to observe how this mated region between the two bars moves to the right. This problem is going to leverage what we've discussed in class about thermal strain and thermal stress resulting from constrained thermal strain, and our previous topics in mechanics, which have included constitutive relationships, compatibility, and equilibrium. If you'd like to see how we might do this problem in a couple of different ways, you can take a look at the lecture that's from the fall of 2024, session 8. And we're going to use the second way or second approach that's described in that lecture. And we're going to focus more on using geometric compatibility than superposition of forces. Now, we might go ahead and draw out kind of three columns on our piece of paper that represent equilibrium, geometric compatibility, and constitutive relationships. With equilibrium, this problem may be a little bit counterintuitive in that we have a force that's going to be the same on the left and the right. Why is that? Well, there's no force being applied in the mid region. So some of the previous examples we've done, we've said, if we look at the force and the displacement, the force being applied at this mid region, and we look at the force and the displacement there, we have effective spring constant is based on two springs in parallel. Well, in this case, we don't have a force being applied in the middle, and these two bars are really acting in series with each other, okay? Because the force is going to be the same in both bars. So we have A to B, the left bar, and B to C, the right bar. If we look at geometric compatibility, okay, with A, B, and now you see it's A, B, C here. If we look at the geometric compatibility of what's happening with the deformation of this region AB and this region BC, what can we say about the overall displacement? Well, the overall displacement between C and A, okay, is going to be equal to the deformation of B relative to A plus the deformation of C relative to B. Okay, and that's what is given by this equation. Now, there are two walls that are constraining the system. So how much will C move relative to A? 0. And that means that these two, right, are going to be the additive inverses of each other, right? So if B or AB moves to the right by some amount, we're going to see that CB is going to cause a shrinking or a negative displacement. Also would be, B is going to be connected to B here, so it's also, this is going to move to the right as well, but now we're talking about these deltas in terms of how much are the bars expanding or how much are they contracting. For the constitutive equations, let's first look at what we know about relationships between force and displacement. And so we might lump these first couple of equations under a category of mechanical constitutive relationships. Nothing about temperature here. So we can say that we have force is equal to K delta. We can say that K is equal to EA over L. Okay? And we can say that the delta F, okay, or displacement or deformation due to force would be force divided by K. We can also look at our relationship for thermal displacement or thermal deformation. And we can say that a delta T would be equal to alpha delta T times L. The strain would be just alpha delta T, right? But we multiply by L, and now we've got displacement. So we're talking about a force-based displacement and a thermal displacement. We're going to end up wanting to combine geometric compatibility and constitutive equations with each other. Before we do that, though, let's take a look at more aspects of geometric compatibility. we can say that the deformation from B to A is going to be equal to the deformation due to the thermal strain or the thermal stress, okay, or the thermal displacement or the thermal loading, you could say, plus the deformation due to an applied force, F. Okay? We can also say that the deformation from C to B will be dependent on a thermal displacement plus a force-based displacement. Okay? And that is a typo. Hold on a second. Or maybe a righto, not a typo, but this should be C to B, right? Like that. Okay. Now, um, once we've kind of established this geometric compatibility, we can substitute in constituent relationships. What are we talking about? Well, we know that thermal displacement is going to just be alpha delta TL. So if we're using the parameters given on the left, we have an alpha 1, we have a delta T, which is for the whole system, and we have an L1, okay, right here. And we also have a displacement based on force. Now, these forces, which are the same on either side, are putting the whole system in compression, right? This thing wants to expand as we increase the temperature. And if that's the case, then the walls are going to be applying a force to resist that expansion. So we can say that there's going to be a force-based displacement that is going to be going opposite of the thermal expansion. Likewise, for the region between B and C, okay, we can say that the deformation of C relative to B is going to be the alpha 2 delta T L2, so the thermal displacement, minus a force-based displacement. Okay, once again, this region B to C is also under compression. We have here relationships for the spring coefficients or spring constants given by E or EA over L, and they're going to be different spring constants for each of these regions because they were given to us with different elastic moduli, different lengths. I think the areas we said are going to be the same though, so we can still have A and A. When we put this relationship and this relationship into this geometric compatibility relationship, we'll have this equation, right? So this plus this is going to be equal to 0. Okay? And we see that the forces are the only unknowns in this problem, or the one force is the only unknown, right? Because we know alpha 1, we know the change in temperature, we know L1, alpha 2, we know delta T, again, we know it's the same, and we have L2, which we know K2 and K1 as well from these equations. So we can rearrange to solve for the force, and we get this expression. And we can then say, look, I know that the change in this midline, or this mating line between the two, this delta moving to the right, is going to be the same as the deformation of BA, or B relative to A. Look at that, right? That's moving there. You could also say it's equal to the negative of the compression, I guess you could say, or the displacement, maybe better said, okay, of C relative to B. So how do we solve for the delta B to A? We just go back to this equation over here, and we can write out that the displacement is going to be equal to alpha 1 delta T L1, okay, which is the same thing, minus F over K 1. So we have to solve for the force, and then we plug it back into this equation. There are a number of parameters, and these equations are not super trivial, and we're kind of going to solve for force first, and then plug it back in. So this is probably a case where let's skip the Google and go right to using a Python script. If you were doing this, with pen and paper, you would go ahead and solve for the force first with your hand calcs, and then you would plug that force into your delta. Okay? But here we go into Colab and importing NumPy to get us started. Control Enter, and now we've got to keep track of a number of parameters that I'm not sure if I can remember. So let's do this. We're going to first write out some values, or variables better said, okay, without numbers, okay, and then we're going to go back to the previous slide and put in some of these values for these variables so that we can calculate things out. So we're going to have an E1 as well, we're going to have E2 as well, we're going to have an area, we're going to have an L1, look at all these parameters, we have an L2, right? And then we're going to have the opportunity to solve for a K1, and that was E1 times A divided by, well, Colab even knows, wow, look at that. In K2, I'll take it if it gives it to me. And we're going to have a force calculation. That's going to be this quantity alpha 1 times delta T. I guess I could distribute the delta T, but I didn't do that. So we'll just leave it like that. Okay, plus alpha 2. Oh, wow, look at this. It's pretty smart. It's not quite right, but it's close. Okay, so that top is now good. Let's come over here, and we're going to 1 divided by K1 plus 1 divided by K2 in the denominator. That should be the force. For the delta, okay, we have our alpha 1 times delta T times L1, and we're going to minus force divided K1, okay? And we're going to print the delta, did they say it's in microns? We're going to, I think it's probably going to end up being in microns, so we'll do NP round, and we'll say delta, and we'll multiply by 1e6. We'll go, yeah, we can go a couple decimal places. Hopefully that's enough. It might not be. We'll see. If it gives a 0, then we'll change it. Okay, and we'll do microns like that. Okay, so now we've got all these equations in here, but we don't have values. So for that, and I'll probably run this and make a mistake, to be honest, but let's go back to the previous slide where we had all the uh-oh, did I do too fast? No, I think we're good. Where we had the numbers. Okay, so here we go. Let's get the Colab here, and let's type some things in. So the alpha 1 is 12 times 1e to the minus 6, so 12 times 1e minus 6. Okay, and that's dimensionless. Alpha 2 was given by 23. Okay, the delta T was 209, okay, K, so we can put K there, it's Kelvin. E1 is 209 gigapascals, so we'll do E9, and we'll just say that's in pascals. And the E1 was 68, like that, all right. The area is 0.8 centimeters squared, so 0.8. And then I'm going to do 1e minus 4 to give it to us in meters squared. L1 is equal to 0.5. And L2 is 0.3. Okay. And have we got, I think we've got all the parameters here. I'm a little nervous about whether or not this is going to work, but why not? Let's give it a shot. So we hit Control Enter. It looks like it ran. I just can't see the result. Okay, and we get 306 microns. and I trust that answer is correct as long as I didn't make a mistake in my input of the equations. At any rate, I hope you find this example helpful, that we have been able to calculate how much to the right this bar goes. And okay, I would normally close right there, but let's just think about what's happening. This is a positive number, okay, this being the delta, okay, which suggests that the left side is winning this push of war, if you will, between these two materials, or two structures, or two bars, if you will, all right? And you notice that the elastic modulus of this bar on the left is a lot higher than the bar on the right. So 209 gigapascals versus 68 gigapascals. Even though the linear coefficient of thermal expansion for the right is twice that of this, on the right is twice of, almost twice, it's 23 versus 12, e to the minus 6. On the right 12, on the left, or on the right 23, on the left 12, e to the minus 6. So, you know, if these were unconstrained, this would have a higher, the right, this, I have to be careful when I say this, the right one would have a higher thermal strain than the left one, okay? And you could even say, well, we know that the displacement, because this is 0.5 meters on the left side, and this is 0.3, this 0.3 is more than half. So you could even say that if they were not connected to each other, if they were both free, that the right one would have more displacement than the left one. Okay, not by much, but by a little bit. Okay, because these are pretty close. I mean, 23 is not quite double, and 0.3, okay, is over half, okay, of the length of the left one. So anyway, so you would have more thermal strain and more thermal displacement, but they would be pretty close, and they would be pretty close. If I mate them to each other, because the elastic modulus of the left bar is higher than that of the right bar, in this push of war situation, the left one wins, and we see a push to the right. In fact, maybe it's interesting, this is unscripted, of course, but if we just think about, okay, this 306 microns, how does that compare to the um, uh, unconstrained, okay, displacement that one of these bars would experience? Well, we can do that. Let's just say delta 1 unconstrained, so that if I ever look back at this, I don't get confused. All right, that would be, yes, that's the equation. Alpha 1 times delta t times L1. Look at that. That's super slick and smart. And then it even knows I want to print this. Wow, Gemini, okay, you're on fire. And does it know yeah, it knows it's in microns too. All right, so what do I get? Well, before I hit Control Enter, I just hit Enter. So, but before I hit Control Enter, will this be less or will this be more than 306 microns? Well, it's got to be more, right? Because this would be the unconstrained displacement, right? The left bar unconstrained, the right bar pushing it to the left. So let's see what we get when we do that. When we do this, we get 1254 microns. So almost 4 times the displacement, okay, if I just had this bar on the left unconstrained. Well, I hope you found this example useful, and you should just be able to, if you're taking the class, be able to upload the answer into the box. There's no finite element on this, and I hope you enjoy. Thank you.